Our second condition for equilibrium is a criteria that necessitates equilibrium involves rotational acceleration. The object cannot accelerate linearly, right? F net must be equal to 0, therefore A is equal to 0. But it also cannot rotationally accelerate. It can't speed up or slow down rotation in any axis. So it has to maintain a constant angular velocity for dynamic equilibrium, just like it can maintain a constant velocity for a dynamic equilibrium. So what causes rotational motion? What causes an object to spin up or to slow down in its rotation? A force that's applied to an object can cause an object to rotate. That force that tries to cause the object to rotate is called a torque, and it's given by the symbol tau. Now, torques are forces that are basically applied that are not through the center of mass of an object. And by center of mass, I mean if you imagine an object where all the material in the object is focused in on a single point, that's the center of mass of the object. It usually has to do with symmetry. So imagine a long ruler stick. The center of mass of that object is the middle of that ruler stick, assuming that the ruler stick is symmetric. The center of mass for me is somewhere down the middle. Right? My legs might be slightly less massive than my torso, so the center of mass might be close to my belly button. But that's the center of mass. If you push me there, I'm not likely to rotate, right? Knock my feet up from underneath me, like a football player coming in for a tackle, or a soccer player coming in for a tackle, you can cause the person to flip. Or a tackle at the shoulders or head can cause the person to turn over. So any force that applies that might cause the rotation is called a torque. Now, torques don't have to cause rotation, because in equilibrium, there should be no rotation. But the torques could cause a rotation, any force that can cause a rotation. And we'll talk about what causes, how to figure out what a torque is in just a moment. So we come back to the example of the merry-go-round. So imagine we are looking at a merry-go-round from above, and we apply the same force, force F, in the same direction to the right, but we do it at different points around the edge of the merry-go-round. Well, here if we start, we'll start with the red. Here we start at the left side of the merry-go-round. We're pushing towards the center of the merry-go-round with force F. Now imagine the merry-go-round is stationary this time. There is a pillar in the middle holding it in place. Would force F cause a rotation? And the answer is no. The merry-go-round would not rotate. Right? If the merry-go-round pillar is over here and here's the edge of the merry-go-round, pushing it towards the center doesn't cause the merry-go-round to rotate. Likewise, on the right-hand side, pulling the merry-go-round, again, with the force going through this center, doesn't cause a rotation. So there's no rotation if you're pushing at these two edges. Interesting, okay. Let's look at the green next. Again, we're pushing to the right, but now we're not on the left or the right-hand side. We're a little bit towards the edge here. So the force is pushing to the right. Would you get some rotation if you pushed at those positions? And the answer is yes. It would actually rotate a little bit. It wouldn't rotate very much, but the object, if you pushed here at the bottom, the object would start rotating counterclockwise. If you pushed up here closer to the top, the object would start, the merry-go-round would start rotating clockwise, but it would rotate. Okay, finally, blue. If we push on either, not both at the same time, but either of these positions, the merry-go-round will definitely rotate. Right? That's how most people use a merry-go-round. They stand at the edge and they shove it to the side, applying a force that's tangent to the circle. This causes maximum rotation. It's the most efficient way to push around a merry-go-round. Now note that the difference between these vectors, again, they're all the same size, they're pointing all the same direction. What's interesting is how they relate to the radius. So each of these black dotted lines is a radius line running from the center of rotation to where the force is applied at the edge of the merry-go-round. See how the radial line here and the force are, in this case, anti-parallel. The radial line comes from the center and goes to where you're applying the force. So the radial line here is pointing to the left, the force is pointing to the right. They're anti-parallel, no rotation. Here, the radial line is pointing to the right. The force is pointing to the right. They're parallel, still no rotation. Well, let's look at the example where there's extreme rotation. Well, at the top here, the radial line is pointing up, but the force is pointing to the right, giving them a 90-degree angle. That gives us maximum rotation. At the bottom, the radial line is pointing down, the force is pointing to the right, giving us a right angle. Again, maximum rotation. And then finally, this green area, this angle is some angle theta. The radial line here is some angle theta. Between those two. Here they're pointing up and to the left. So actually the angle would be, that would not be theta, sorry. This would be theta. A little less than 180 degrees, here a little bit more than 180 degrees. Almost 360 degrees. So what's the relationship between the force and this radial line from the axis of rotation? Well, that is the key. It's one of the key pieces of information. If we're at 90 degrees, we get maximum torque. If we're at 0 degrees or 180 degrees, we get nothing. Well, there's actually a trigonometric sign that allows us to do that, right? Sine of theta, if theta is 0, like it is here, sine is 0, so there's no torque. If theta is 180 degrees, so here we have r moving out in this direction. Here's theta, it's 180. In that example, plug in sine of 180 degrees, you get 0. There's no torque. Sine of 90 or 270 degrees will give you the maximum amount of torque. The torque depends on the force, right? No force, no torque. That hopefully makes sense. If I'm not pushing on the merry-go-round, it's not going to start spinning. And then finally, it depends on the size of the radius. And that's an important bit of information. The bigger the radius of this merry-go-round, the bigger the merry-go-round, the more torque you produce at a given force. Now, what do I mean by that? Well, some of you might be like me, where you're exiting a store and you're not sure what side, you see the big push bar, and you're not sure what side the hinges are on. The hinges provide the axis of rotation for the door. So you walk up to one side of the door, you hit the bar, and it's like boom, you get bounced back, and the door only opens a little bit. You sigh to yourself, you're like, oh, I'm an idiot. You move to the other side of the door, you press, and the door easily opens. Even though you apply the same amount of force in both situations, the torque on the door that causes the door to spin or open also depends on the radius. Right? When you go to a door, the door handle is always on the opposite side of the hinges, because pushing on the hinges doesn't open the door. So this is the equation for torque. Torque is equal to how far away from the rotation axis are you applying the force, how big is that force, and what is the angle between those, right? If you go up to a door handle, you always push a door, if you have some door here, right, you always push perpendicularly to the width of the door, right? You don't push the door to the side. You don't try to push the door into the hinges. That makes no sense. So this is torque. Torque, we'll learn in the next chapter when we talk about rotation. Torque causes angular acceleration, just like forces cause linear acceleration. Now the unit for torque, sine has no units. R, the radius, is in meters. F is in newtons. So the SI unit for torque is the Newton meter. Now, we've talked about Newton meters before, right? Work is force times distance. Force times distance is Newton meter. Work is measured in joules. Torque is not. even though it has identical units to work, work is measured in joules, work is related to energy, torque is not. And the big reason they're different is torque is actually a vector. It depends upon, there's a direction to the torque. You can create a clockwise or counterclockwise rotation depending on where your forces are. For example, this force down here, if I applied it, will cause this to rotate counterclockwise. If I applied the same force up here, this would cause it to rotate clockwise. Counterclockwise rotations are positive. Clockwise rotations are negative when you are applying torques. So torques that would produce a clockwise motion are negative. Torques that would produce a counterclockwise motion are positive. This becomes incredibly useful when you are adding torques together, because in equilibrium, not only do the forces have to add up to 0, but the second condition of equilibrium states the net torque must also be 0. When you add up all the torques on a system, on an object, for that object to be in equilibrium, all those torques have to add to 0. So as many torques are trying to push the object counterclockwise as clockwise. The same strengths between the two motions, canceling them out, giving you 0 net torque.